Hello and welcome to another video with Leah. Today I'm going to be doing another exam review. Topics included are Lewis structures, resonance structures, polarity, formal charge, bond properties, and more. I really hope you enjoy this video, and if you're new, don't forget to subscribe and click the little bell so you can know when I post new videos. How many valence electrons are in dinitrogen trioxide, N2O3? So we need to count the valence electrons. And for this, we can use this pattern. So here's a quick sketch of the periodic table. And we know that the elements in this first group have 1 valence electron. Going on to the second group, they have 2 valence electrons. Elements in the 13th group here, or third group if you subtract 10, have 3 valence electrons. Elements in the fourth group have 4 valence electrons, elements in the fifth have 5 valence electrons, and so on and so forth. And you just note that over here you subtract 10, so you can get the correlation between group number and number of valence electrons. Now let's look at a periodic table. Nitrogen is in the group 5. So nitrogen has 5 valence electrons, so VE valence electrons, but there are 2 nitrogens. So what we're going to do is multiply 5 times 2. Okay, and this is going to give us 10 valence electrons. Now for oxygen, we notice that this is in group 6. So each oxygen has 6 valence electrons. But there are 3 oxygens. So to get this, we need to multiply 6 times 3, which gives us 18. So in total, there are 10 valence electrons from nitrogen and 18 valence electrons from the 3 oxygen atoms. Now we're going to add these numbers up, and that will be 28 valence electrons for this molecule. For the next 3 molecules, draw the Lewis structure and determine the molecular shape and the electron pair geometry. First we have NO2-. Our first step in drawing the Lewis structure is to find the total number of valence electrons for this molecule. So as we said before, nitrogen has 5 valence electrons, plus oxygen's valence electrons. So each oxygen atom has 6 valence electrons. However, because there are 2, we'll do 6 times 2 for oxygen. And then this molecule has a overall negative charge, so we add another valence electron. So 5 plus 12 plus 1, that is going to be 18 valence electrons. Next, we are going to draw the skeletal structure, so the central atom, and bond the outer atoms via a single bond. Nitrogen will be the central atom, to which we will attach 2 oxygen atoms. Now in this structure, we have used 4 valence electrons, because remember, one bond, or one line, is equal to 2 valence electrons. So we already used 4, so we have 14 left. We will start putting the 14 valence electrons around the outer atoms first, so 2, 4, 6, 8, 10, and 12. Now we notice we have 2 more valence electrons, which we will then put on the central atom. Our next step is to check if the octet is fulfilled for these 3 atoms. Let's check the oxygens first. They look the same. They each have 3 lone pairs of electrons and 1 shared pair. Counting up the number of valence electrons, we see 2 in the bond plus 6 lone electrons. That equals 8 valence electrons. So oxygen is satisfied in its octet rule. Let's check nitrogen. So nitrogen has 1 lone pair plus 2 bonds. So that is 6 valence electrons. But nitrogen wants an octet, so we need to make a double bond somewhere. We can choose these 2 valence electrons and transfer them to make a double bond here. Okay, and I will erase the transfer because these have moved. Right, so now those 2 electrons that I just moved are shared between them. So they apply to nitrogen and they still apply to the oxygen because they are shared. We could have also taken the electrons from this oxygen, the one on the left. Either one works fine, just as long as the octets are filled for these 3 atoms. So in the end, this will be the structure for NO2-. For this question, we also want to find the molecular shape and the electron pair geometry. So let's start off with the electron pair geometry. Electron pair geometry counts the number of lone pairs plus the number of connections or links that the central atom makes. So in this example, we have one lone pair, we have one connection on the left, and we also have a connection on the right. So this equals 3. So a number of 3 groups around the central atom indicates a trigonoplanar geometry. Notice that we are not counting bonds. We're not counting the number of bonds. We're counting the number of groups around the central atom, which is why we counted the double bond as just one group, not 2. Now let's find the molecular shape. And molecular shape only counts the number of connections that are attached to that central atom. So not the lone pairs, just the connections. So we're looking at this right here and this right here. And molecular shape also has to account for the lone pairs. Now a combination of 2 atoms around the central atom plus 1 lone pair indicates something we call bent. Okay, so the molecular shape is bent and the electron pair geometry is trigonoplanar. Now with perchloric acid, let's find the Lewis structure, the molecular shape, and the electron pair geometry. First, we need to find perchloric acid's formula, and that is going to be HClO4. Okay, so 1 hydrogen, 1 chlorine, and 4 oxygen atoms. Now let's draw its Lewis structure. So our first step in drawing the Lewis structure is to count the number of valence electrons. Hydrogen has 1 valence electron, chlorine has 7 valence electrons, and then we have 6 valence electrons for each oxygen, but we have to multiply by 4 because there's 4 oxygens. Okay, so this is 8 plus 24, which is 32 valence electrons. Now we will draw our skeletal structure. So we will have chlorine in the center, and we will bond 4 oxygen atoms around it. And we'll attach the hydrogen to one of the oxygens via a single bond. Now in our skeletal structure right here, we just made 5 bonds, and that correlates to 10 valence electrons. Now we have 22 left. With these leftover valence electrons, we will start putting them around the outer atoms first. So 2, 4, 6, 8, 10, 12, 14, 16, 18. And then we have those other ones which we will put around this oxygen, 20 and 22. Notice that I did not put any valence electrons around hydrogen because it can never have lone pairs around it. It can only make a single bond in these Lewis structures, and that's it. Okay, because hydrogen only can fit 2 valence electrons max, which it gets by making 1 bond. Now we have our preliminary structure with all of our valence electrons drawn out. Now we will be getting to formal charge, but I just wanted to say that we need to move these electrons to make double bonds around the chlorine. Right, so from the 3 oxygens, we need to make double bonds. Notice we're only making the double bonds with the oxygens that don't have the hydrogen on them. Alright, so these will make the double bond, right, and I will erase the transfer as those electrons just move to make a double bond. We made these double bonds so that the chlorine and these 3 oxygen atoms have a 0 formal charge. Before, these 3 oxygens had a -1 formal charge, and now they're at 0. And this chlorine, it used to be a +3 formal charge, and now it's at 0. So this is the structure that we want. Now let's answer the questions about the molecular shape and the electron pair geometry. Let's start off with the electron pair geometry. So for chlorine, we need to count its number of groups around it, the number of atoms, and the number of lone pairs. Now, there are no lone pairs, so we know that the molecular shape will also have the same name as the electron pair geometry. So really, we just have to find one of the names. And for that, something that has 4 atoms around it and no lone pairs, we call that tetrahedral. Tetra for 4. Like I said, the molecular shape is also called tetrahedral. Let's do the same thing now using phosphorus pentachloride. Phosphorus pentachloride has the formula of PCl5. Let's find the number of valence electrons for this compound. Phosphorus has 5 valence electrons, plus 7 for each chlorine. And there are 5, so we need to multiply 7 times 5. So 5 plus this right here, which is 35, equals 40 valence electrons. Now let's draw the skeletal structure. So we will put phosphorus in the center and attach via single bonds the 5 chlorine atoms. Doing this, we just used 10 valence electrons, so now we have 30 left. With these 30 left, I will start putting them around the outer atoms first. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, and 30. So all of these valence electrons were used by putting them around the outer atoms. Now we have no more valence electrons to draw. Now let's check the octets. So these chlorines all have their 8 valence electrons. They have their octet filled, okay, from the 1 bond and the 3 lone pairs of electrons. This phosphorus in the center has 10 valence electrons because it made 5 bonds. And we know that's okay because phosphorus is an element that can have an expanded octet. Expanded octet meaning that it has more than 8 valence electrons. Alright, so this is the structure for PCl5. Now let's find the molecular geometry and the electron pair geometry. Notice that phosphorus has no lone pair electrons around it. And again, as mentioned before, this means that the molecular shape name will be the same as the electron pair geometry name. So something with 5 atoms around it and no lone pairs is called trigonal bipyramid. And this is the name that we will call the electron pair geometry and the molecular shape. And just as a quick note, molecular shape can also be called molecular pair geometry. They're both the same thing. Next question. What is a coordinate covalent bond? To answer this question, I will also show a covalent bond. Let's do the covalent bond first. So this is the one on the left. When 2 hydrogen atoms bond, as in the molecule H2, the bond they make has 2 electrons. And these 2 electrons are from each hydrogen. So one hydrogen contributes 1 valence electron, and the other hydrogen joins and brings its own valence electron. And these 2, they're going to be part of this one bond. So a covalent bond means that the bond is made up of 1 electron from one atom and another electron from the other atom. Let's compare this to a coordinate covalent bond. Now it's still covalent, so it's still between nonmetals. But let's use this example. So this example on the right says ammonia and boron trifluoride. So ammonia has the structure of the nitrogen atom in the center, along with the 3 hydrogens, and a lone pair of electrons. You can try to find this structure on your own and see if you get the same answer. Now next, for boron trifluoride, that looks like boron in the center, and the 3 fluorines around it. And boron has no lone pairs around it. The difference between a coordinate covalent bond and a covalent bond is this. In a coordinate covalent bond, these 2 electrons that are going to form a bond come from the same atom. Alright, so these are going to be shared and they're going to make this bond. And I'll just make this right here. They're going to make the bond so that in the end you have this right here. Now it's important to note, one bond is 2 valence electrons. Okay, that's all. No more, no less. And so in this bond, we just saw that the 2 electrons, that bond was only made up from electrons from one of the atoms. Whereas in this example, the bond is made up from electrons from here and here. So from 2 places. So a covalent bond has electrons from 2 atoms, and a coordinate covalent bond has electrons from 1 atom. Isoelectronic species have the same blank and the same blank. So this is the same number of electrons, so I'll just put number of electrons. And they also have the same Lewis structure. What is the difference between an ionic and a covalent bond? An ionic bond is between a metal and a nonmetal, and the electrons are transferred so that one atom becomes a cation, meaning positively charged, and the other becomes an anion, meaning negatively charged. A covalent bond, on the other hand, is between 2 nonmetals, and the electrons are shared in the bond. Describe the difference between core and valence electrons. Let's imagine an atom Alright, and let's also think about electron configuration and noble gas configuration. For this example, let's take the electron configuration of carbon. So carbon has 6 electrons, so its electron configuration was 1s2, 2s2, and 2p2. Valence electrons are just the electrons in the outermost shell of an element. So for this, the electrons in shell number 2, or level 2, would be the valence electrons because they are in the outermost shell. The core electrons are part of the noble gas that came before carbon. And if you look at a periodic table, you will see that helium was the noble gas before carbon. And helium has 2 electrons, and its electron configuration is 1s2. The core electrons for carbon are what are included in the previous noble gas, and the valence electrons are the ones that are not included by that previous noble gas. They are in the outermost shell and are thus called valence electrons. Find the formal charges for all elements in the phosphate ion. Phosphate ion is PO4, -3, and the number of valence electrons it has is 5 from phosphorus, plus 6 per each oxygen, so we'll multiply this by 4, plus 3 because of its negative charge. So this is going to be 5 plus 24 plus 3. This will be 32 valence electrons. Now let's draw its skeletal structure. So the central atom connected to 4 outer atoms, these oxygens. Making 4 bonds, we just used 8 valence electrons. Now let's place these remaining 24 around the outer atoms first. Okay, so 6, 12, 18, and 24. Now after this, we're going to make 1 double bond. Okay, so we'll just choose any oxygen. It could be the bottom, the top, or the left or the right. And we will make a double bond, and I'll erase the transfer. Now these electrons are shared. Right, so we make this double bond so that phosphorus can have a 0 formal charge, and one of these oxygens can have a 0 formal charge. Now let's find the formal charges for this compound. Now, how do we find formal charge? Well, I'll use Fc as formal charge, and you might have seen this formula. It's the number of valence electrons minus the number of lone pair electrons minus half the number of shared pair electrons. Now, this is kind of messy, alright, so I like to simplify this. Okay, so we will erase this. For me, formal charge is number of valence electrons minus lines minus dots, which means the number of valence electrons minus the bonds minus the lone electrons. Okay, but this is like the simplest I could get it down to. So number of valence electrons for that element minus the number of lines it has around it minus the number of dots it has around it. And the great thing about this is that it still equals the same thing as you would have got using the formula that I had shown before. Now for phosphorus, phosphorus has 5 valence electrons. So we will subtract the number of lines around it. Well, it has, let's see, 1 line here, 2 lines here, 3, 4, and 5. Okay, so we're counting the number of bonds around it. So 5 minus 5 equals 0. So phosphorus has a 0 formal charge, which is excellent. That's what we want. We want our elements to have 0 formal charges, or as close to 0 as possible. Now let's find the formal charge of these 3 oxygen atoms, the ones with 3 lone pairs and 1 bond. The number of valence electrons for oxygen is 6. The number of lines for each is 1. The number of dots around each is 6. So we do 6 minus 1 minus 6, that is -1 for the oxygens in purple. Alright, and lastly, we will do the formal charge of this oxygen down here. They made 2 bonds and has 2 lone pairs. So this oxygen down here has 6 valence electrons minus the number of lines, so 2 lines minus the number of dots, well 1, 2, 3, 4 dots. And 6 minus 2 minus 4 is 0. And this is for the oxygen in blue. Alright, so phosphorus has a 0 formal charge, the oxygens in purple have a -1 formal charge, and the oxygen in blue has a 0 formal charge. And if we add all of these formal charges up, in total we have -3, which is the charge of our ion. And it's -3 because we have negative here, and negative here. Each of these oxygens has a -1 formal charge. This has 0, and this has 0. Show the resonance structures for the sulfate ion. First step is to know its formula, so sulfate is SO4, -2 charge. Let's draw its Lewis structure. So we'll put the number of valence electrons is 6 plus 6 times 4 for oxygen, and then plus 2 because of the -2 charge, and the 6 is from the sulfur. So this is 32 valence electrons. Now let's draw our structure. So we will put sulfur in the center and connect it to 4 oxygen atoms. If we make 4 bonds, we used 8 valence electrons. So we have 24 left. And these 24 will go on the outer atoms first. 6, 12, 18, and 24. Okay, so no more valence electrons to use. Now we want the formal charges to be closer to 0, or basically at 0. So what we're going to do is make double bonds. So let's do this transfer over here and draw another 2 from over here. So now we have 2 double bonds, and I'll erase the transfer. And if you calculate the formal charge for each element here and you add them up, in total you'll get -2, because these 2 oxygens, okay, have a -1 formal charge, and then these 2 oxygens have a 0 formal charge. And the sulfur in the middle has a 0 formal charge as well. You can calculate this on your own for practice. Now, we could have drawn either this with a -2 charge. Remember, resonance structures have this double-headed arrow between them. The other resonance structure could have been with the double bonds from the top and bottom oxygens. So still, the sulfur is in the middle. And then you have the double bonds here. Right? Okay, and this would have also worked. And this would still have a -2 charge. So just remember for resonance structures that you're moving electrons within the same molecule and that the charges in total need to be the same. Okay, you don't want to draw resonance structures with different charges. Now, because this is a tetrahedral electron pair geometry and shape, you could have also drawn the double bonds adjacent to each other. So instead of being opposite to each other, you could have drawn them in, flat surface, like could have been something like this and this, or this and this, or this and this, or this and this. Okay, and then just arrange the lone pairs around it accordingly. Okay, so those work too, because in tetrahedral geometries, basically it's 3D. So one oxygen's going back, and one is going forward, and then these 2 are in the plane. And what you see is that between all of these oxygens, you have the same bond angle. Okay. So even if in 2D it looks a little bit different, well, in 3D it's actually just the same. Think about the structure for methane, which is CH4. Okay. It's also tetrahedral, and it also has the same shape. So between all of these oxygens, it's the same bond angle. So it doesn't really matter in 2D where you put the double bonds. They're still going to be the same distance away from each other. You can see this even more clearly if you build a little model of it. So if you get this little molecule kit, and they have like oxygen atoms and bonds and sulfur atoms, and you connect them, you will see that the oxygen atoms are all the same distance apart from each other. What is electronegativity? And what is its periodic trend? So electronegativity is the ability of an atom, of an element basically, to draw electrons toward itself. Okay, so to attract those electrons towards it. And its periodic trend goes something like this. So as you go to the right, okay, and as you go up, the electronegativity values will increase. Right, so it's just that ability of that atom, okay, to pull electrons toward itself. Determine which are polar molecules and if they have polar bonds. So the first one is CH3Cl. Pause the video and see if you can draw the Lewis structure for this. And then come back and we will move on with this question. Alright, so for this you have the central atom is carbon, and alongside it are the hydrogen and the chlorine atoms. Now, if you check the values of electronegativity for chlorine and the electronegativity value for carbon, you will see that the chlorine has a higher electronegativity value. And so that means electrons are more likely to spend time around the chlorine than around the carbon. Okay, so this dipole moment is going towards the right, towards the chlorine. Now let's check the other bonds. Between the hydrogen and the carbon, carbon has a higher electronegativity value than the electronegativity value for hydrogen. So these dipole moments will go towards carbon. However, this one is much more stronger. And as you see, it's not really canceled out. There's no symmetry to cancel out. So yes, this pull will be a net pull in this direction and will make this molecule polar. Now let's try another one, BF3. Now again, pause the video and see if you can find the structure for boron trifluoride. Boron is the central atom along with the 3 fluorine atoms around it. And again, we want to determine if there's polarity in this molecule in total. Now let's see here. So check the fluorine electronegativity values and the boron electronegativity value. You will find that fluorine has a higher electronegativity value, so the electrons are going to want to hang out towards it. So this is the direction of the dipole moment, okay, towards fluorine. Okay, those electrons are going to want to go towards fluorine. Now notice in this structure that it's a trigonoplanar molecular shape and electron pair geometry, meaning that it is symmetrical. And in symmetrical cases, these dipole moments, they're all opposing each other, so they're all going out, basically canceling out each other. And so in total, boron trifluoride is a nonpolar molecule. So even though this, these bonds we would say are polar, well, in total, because they cancel each other out, it's a nonpolar molecule. Next we have NH3. So again, pause the video and see if you can find this structure. For this, we have nitrogen in the center connected to 3 hydrogen atoms and a lone pair on nitrogen. Now, you can check the electronegativity values for these 2 atoms, so nitrogen and hydrogen, and you will find that N has a higher electronegativity. Okay, so those electrons are going to want to hang out towards nitrogen. Okay, so there's a net upward force. Okay, and there's really nothing that cancels it out. Okay, there's no symmetry. This molecular shape would be called trigonopyramid, okay, and there's no symmetry to it. So ammonia is a polar molecule. Now let's do SF2. So SF2 has sulfur in the center, along with the fluorine atoms, and 2 lone pairs on the sulfur atom. And we want to know if this is polar or nonpolar. Well, check the electronegativity values again for sulfur and for fluorine, and you will see that the fluorine has a higher electronegativity value, meaning that electrons want to hang out more around fluorine. Okay, so the dipole moments are this way. Now, in reality, this is a bent molecular shape. So really it's like this. Okay, and the pull is going towards fluorine. Okay, so downwards, basically. Okay, and so this net downward force is making this molecule polar. Now for our last one, CO2. So we have carbon attached to 2 oxygens. So again, check the electronegativity values and you will find that oxygen has a higher electronegativity. Okay, so the electrons are going to want to go towards oxygen. But as you see, this molecular shape is linear. Something with 2 atoms around it is linear without any lone pairs. And you see that these dipoles are basically going in opposite directions. Okay, so they're definitely canceling each other out. Okay, so CO2 is nonpolar. Find the bond order in each of these molecules, O3 and AsCl3. And our bond order formula is the number of electron pairs between the atoms of interest and the number of connections. So how many times is that atom connected to that other atom? So we have 2 molecules. So let's do the one on the left first. So bond order for this, well, the number of electron pairs is, we have 2 right here and 1 right here. So 3 electron pairs. And we need to divide this by the number of connections. So how many times does oxygen to oxygen happen? Well, it happens here and it happens here. So 2 times. Okay, so the bond order is going to be 3/2 or 1.5. Now let's do this for AsCl3. So the number of electron pairs between arsenic and chlorine is 3. 1, 2, 3. Okay, so 3 pairs, and we will divide this by the number of times we see As to Cl connection. So this happens 3 times. Okay, once here, and once here. So 3 divided by 3 is 1. So the bond order for this is going to be 1. So bond energy is something, and bond length is another thing. So bond energy is the energy needed to break a bond. And bond length is kind of self-explanatory, it's just the length of that bond. So how long it is. For carbon dioxide, how many sigma and how many pi bonds are there? Alright, so let's look at the bonds. Remember, a double bond has 1 sigma bond and 1 pi bond. So if we count this, the green ones are the sigma bonds, so we have 2 sigma bonds, and we'll write its symbol. And we'll count the number of pi bonds, so the ones in blue. So we have 2 number of ones in blue, so 2 pi bonds. Okay, so CO2 has 2 sigma bonds and 2 pi bonds. Find the hybridization of the central atom in ammonia. The hybridization is basically the number of groups around ammonia, and is based upon the electron pair geometry, so counting the number of bonds and the number of lone pairs. Nitrogen, 3 bonds and 1 lone pair, and adding these groups up, that is 4 groups. Now 4 groups makes a tetrahedral electron pair geometry, and electron pair geometries that are tetrahedral all will have a hybridization of sp3.